Welcome to this video on linear approximation and Newton's method. So what we will do in this video is approximate a function by its linear approximation, that is a local approximation, basically the tangent line to the graph. And we will use this first to approximate function values for complicated functions. And in the second place, I will sketch a method to find the zeros of a function. Now, in the previous video, we've already seen that you can use bisection there, and I'll quickly repeat that. But bisection is quite a slow method, and the standard numerical method to find approximations of zeros of a function is called Newton's method. And if you have a calculator, and you can have your calculator find the intersections with the horizontal axis, so basically the zeros of the function, then it will use some version of Newton's method. And we will outline that in this video. So let's have a quick outline of what we will see in this video. So I will first talk about linear approximation, then I will sketch again the problem of zero finding. I will repeat bisection, and then I will show you how Newton's method works. So first, let's say that we have some function. I've sketched here some y is f of x, and we pick a point on the graph. So we pick the point P, which has x coordinate x0, and because it is on the graph, it means that the y coordinate will be fx0. Now what we can do is find the tangent line. So the black line here is tangent to the graph at the point P, and we know that it will have slope f prime at x0, so we have to compute the derivative and evaluate that at x0. Then P is a point that lies on the straight line, so this will be the formula for the straight line. And if we rewrite that a little bit, we see that the straight line has this equation. So it's f prime x0, that's the slope, times x minus x0 plus fx0. And now the idea is that locally, as you see here, if you're close to the point P, so for x values around x0, the black line will be a good approximation of the graph. So we call that the linear approximation. And if we want to find values of fx0, and it's complicated to compute f of x, then we can use this tangent line as an approximation. So here I called that line capital L of x for linear approximation, and this is just the formula of the tangent line as we have just seen. So how can we use that? Let's look at two examples. First example is the cubic root. So we are asked to find a linear approximation to approximate the cubic root of 8.02. So what we are looking for is the value y such that y to the power 3 equals 8.02. Now, of course, we know that 2 to the power 3 equals 8. So we expect this y value to be approximately 2, but not precisely. So if you want to use linear approximation for this, I am going to look at this graph here. So y is the cubic root of x, and I am going to expand that close to x equals 8. So I define the function f of x is the cubic root of x. I'm going to use that f of 8 equals 2. I can compute the derivative, so I have here this thing here is x to the power 1/3. So if you differentiate, you get 1/3 times x to the power minus 2/3, and that's precisely what you find here. So the tangent line here has slope this function at x equals 2. And then I can use that x equals 8, y equals 2 is on the graph. So let's use that. The linear approximation of f at x equals 8 is Lx, and I just use the formula, so f prime at 8. So this function evaluated for x equals 8 times x minus 8 plus f8, and f8 equals 2. Now, if you do the simplification here, then you find that it is 1 over 12 times x plus 4 over 3. So this is a lot easier than computing the cubic root, if you would, for instance, have to do it by hand. So let's see how good this is. If you now plug in 8.02 into this linear function, you would find numerically 2.001667. And of course, since we have calculators and we have computers, I also did it on my computer. And if you find the real value rounded, then you see that it is actually quite close. They agree in all digits, only the last digit here is different. So this is a very good approximation, and to compute this value is a lot easier than to compute this value. Another example, let's consider this question. So give a linear approximation of the sine function. So we are interested in y equals sine of x, or fx equals sine of x. And we want to know what is the linear approximation, so a straight line at x equals 0. So we're going to draw the tangent line at x equals 0. So here's a picture. In red we have y equals sine of x. In black here we have the straight line, and that turns out to be, or we will find that that is y equals x. And you see that locally, indeed, it's quite a good approximation. So for small values of x, they are quite close together. For small values of x, sine of x is approximately equal x. And that shouldn't come as a surprise, since we have already seen the standard limit sine of x over x goes to 1. So this also tells you for values of x close to 0, not equal to 0, sine of x and x are very much alike, very close together. So here we also find that using linear approximation. So I define the function fx as sine of x. I compute the derivative at 0, so f prime x is the cosine. If you plug in x equals 0, you find 1. f0 is 0, so that means that the tangent line has the equation Lx equals x, or y equals x, as I already sketched in the graph. So the conclusion is that sine of x is close to x, is approximately equal to x for x near 0. Of course, for x equals 0, it also holds, right? Because sine of 0 equals 0. So this is one of the ways that you can use linear approximation. There is one more thing I like to sketch, which is that you can use it for zero finding. So what is zero finding again? Say that we have a general function y is f of x, and we are interested to find where it crosses the horizontal axis. So we would like to find alpha such that f of alpha equals 0. We want to find a 0 of the function. Sometimes it's easy. If you have a straight line, you can easily compute where it intersects the horizontal axis. If you have a parabola, we have the standard ABC formula, so there we can also do it. But even for very simple equations like this one, so the function 2 times x times e to the power x minus 1, if you want to know where this equals 0, you will not find a nice analytical expression. So what can we do? Well, we've already seen that you could use bisection. So here's a general function, y is f of x. You try to locate an interval ab such that the function is negative at one end and positive at the other end. And if you know that and you have a continuous function, it needs to cross the horizontal axis, and it will cross so at a 0 of the function. And then what we did, we have seen this before in a previous video, we look at the midpoint of the interval, so m is a plus b over 2, and we consider what the function value is at this point. So here it is positive, which means that we can shift b to m, and then we effectively shrink the size of the interval that contains alpha. If fm would be negative, that's not what the picture shows, but then we could move a to m, and if we would find fm to be equal to 0, then we're done, we have found a 0. And you repeat this procedure and you shrink the interval. And if you do that, for instance, for this problem, this is a parabola. There are two zeros, square root of 3, minus square root of 3. This you can find by punching it into a calculator, the approximate value of square root of 3. Let's say that we want to find that using bisection. Then you could start with the interval 0, 2, because f0 is negative and f2 is positive. So this is a good interval. It contains 0. Of course, we also know that because square root of 3 is 1.7, and that's in between 0 and 2. And then if I make a little table starting with 0 and 2, computing the midpoint, and then checking the function value, and in this case shifting a, and if you keep on doing that, you see that a and b get closer together. This will converge to alpha square root of 3, and you see indeed that this is already getting closer to 1.73205. And you also see that the function values are shrinking. So this is a method to find a 0. I went through it quickly because we have seen it before, but the convergence is quite slow. So you need quite many steps if you want, say, the first 10 digits to be correct. Using linear approximation, we can do this better, and that is Newton's method. So what Newton did is the following. He said, well, say that we have some idea where the 0 is approximately located. A starting guess, x0. What you do now, so here we have a function and we would like to find this point alpha here where it crosses the horizontal axis. Here x0 is our initial guess. And what I'm going to do is I'm going to draw the tangent line. So I'm going to use the linear approximation. That's the blue line here. And where the blue line crosses the horizontal axis, that is going to be my next approximation. And as you see, it's already moving towards alpha. And I can repeat this. So I can say, well, let's do this again. At x1, I'm going to draw the tangent line, which is in green here. I have only shown part of it because otherwise the picture gets a bit messy. And where it crosses the horizontal axis, I find x2. So I'm going to create x values, x0, x1, x2, and so on. And hopefully they converge to alpha. Now here for this picture, x2 is already very close to alpha, and I couldn't plot x3 there, but I simply do not have space. It suggests that the convergence is much faster than for bisection. So let's reconsider the example with the parabola, so going to look for square root of 3. But to do that, I need to have some kind of equation to find xi plus 1 from xi. Given x0, how do I find x1? And drawing the tangent line and finding the intersection, well, that's a bit hard to program. So what you should do is you should find the tangent line. Well, we've already done that. So we've already seen that the tangent line has the equation here. This is the very same that I had on the first slide, but written a little bit differently. Then I have to find where it intersects the horizontal axis. And then what you find is that x1, so the new x value, is the old x value minus fx0 over f prime x0. So that's what you find if you find the equation for the tangent line and see where it crosses the horizontal axis. And this is something that I can easily put into a computer program. So I've done that. And if you apply that to our example, so this is the same example as we did with bisection, then you have this formula. So that's the general formula that we just found. So for our example, what we find is xi plus 1 equals xi minus, well, fxi, that's xi squared minus 3 over, and then f prime. Well, if we differentiate this thing, we get 2x. So here we get 2xi. So apparently if you repeat this, starting with some x0, compute x1, then plug in x1 to compute x2, and so on, then it should go to alpha, to square root of 3. So let's see what happens. So here you see we start with 1, and then apparently the next approximation we find is 2, and then 1.75. And you see that already from the 5th until the 6th iteration, so x5 and x6, they're already very close together here. They only the only difference is in the last digit. So this gives very, very fast convergence. So now we have seen two numerical methods to approximate the 0 of a function, bisection and Newton's method. Bisection, that will always work. You will always find a zero of your function, but it's quite slow, so you need many iterations. Newton's method, well, it doesn't always converge. You can also move away from your zero. If it works, it's very fast, so it uses few iterations. Here on the left, you would only need function values. For Newton's method, you also need the first derivative. So that can be a disadvantage in some problems if you need to find a zero. So that brings me to the end of this video. So what have we seen? We have seen that you can use the tangent line to a graph to approximate function values close to that point. So only locally it's a good approximation. If you move further away from where you make the linear approximation, then it will not be so good. And we have seen two numerical methods to find the zeros of a function: bisection and Newton's method. That wraps it up for this video, and I'll see you in the next one.